Okay. All right. So this talk is actually given in the true spirit of this being a workshop. Everything that I'm going to show you today is very preliminary. This is work that I've been working on with a couple students of mine at Colby College, and both of them are sitting in the back there. So I encourage you to talk to us throughout the rest of this conference about any of our results. And what we've been doing is actually looking at some of the high-resolution simulations. In this talk, what we're focusing on is the HydroArt simulations of Daniel Severino et al. And looking at the structure of these simulations from the observer's perspective. So we've gone in and used sunrise to process the images and produce realistic-looking images that we can then go in and use observer tools like GalFit to look at the structure of these galaxies. And what we're hoping to do is a number of things, right? We want to look and see whether the simulations are producing realistic galaxies, but we'd also like to, in the end, use these simulations to inform our observations and to actually get physical information out of what we're seeing in the observations. And so I just wanted to point out that I think that this is a fairly unique era that we live in today, where we've made several advances, both in observations and on the theoretical front. So observationally, we now have surveys like CANDLES, where we're starting to get these extremely high-resolution imaging and very sensitive images at rest frame optical wavelengths. So throughout the course of this conference, all of the observations that we've been talking about, all the structure that we've been talking about in these galaxies at redshift of 2 were previously hidden to us. So CANDLES is really improving the observational front. And then likewise on the simulation front, now we have projects like Agara that Joel just talked about, where we have now several fully cosmological simulations with extremely high resolution. We can start to take these simulations and produce realistic looking images with them by processing them with sunrise, and then now doing the direct comparison for high resolution structure from both the simulations and the observations. So some of the important results that we've seen from observations is this idea of there's this population of very compact galaxies at early times. And this has been known for a while. We've known that passive galaxies in particular are much more compact at early times. But I like this picture that Guillermo painted. This is sort of the first time we've had this evolutionary idea of perhaps where these compact quiescent galaxies come from, which is that if you take star-forming galaxies and they undergo a highly dissipative event, and we get something that's a very compact star-forming galaxy. So they shrink first and then quench rapidly and move up into this compact passive regime. And so there's the other possible path, which is to sort of quench and then shrink as well. And Guillermo likes to refer to these as the fast track or the slow track. So this is one observational result, and we'd like to see whether this agrees with simulations. And people have talked about this earlier in the conference, so I'm not going to focus particularly on this. But we do see in general from observations that galaxies evolve from to higher Sursok Index, rounder, more bulge-dominated systems as time evolves. And so in general, we need to make sure that our simulations are doing the same thing. So the theorists in the audience like to make very beautiful movies of their simulations of the density of gas. And so from the observer's perspective, I actually wanted to see what these galaxies looked like from stellar light. And so what I did was sort of make a stop motion type animation of all of the sunrise processed images for one particular simulation. And I pasted them together into a movie. So let's see what that looks like. Go over here. So starting from very high redshift, and moving in. And of course, it's not as nicely put together as the real movies. Like I said, it's sort of a stop motion animation. We start with very irregular structure until we get down to relatively low redshifts. Now we start to see the emergence of a spheroid. And then the common theme among many of these is that we sort of see the regrowth of a disk at later times. So let me just play that one more time for you. So lots of irregular structure at high redshift, lots of star formation happening, very chaotic, very violent.
Notice how elongated.
And very elongated, yep.
These are the radiative feedback.
This is with radiative feedback, yes.
Those tend to be on, as Daniel was saying.
Yep, so that's right. Daniel will talk about the elongation of these a little bit later. All right, so that's what they look like in terms of their stars. And so we were using these images and actually going through and using GELFIT to analyze the structure of these images at various time steps. So here's an example. First thing and the easiest thing that we can do is to look at the Sursok Index of these simulations over time. And so what I'm showing you here on the left-hand side, I'll show you plots of the high-resolution simulations. And on the right-hand side, I'll show you plots of the simulations as they've been degraded to replicate candles-like data. And when I say candles-like data, I'm actually talking about the wide field candles imaging, not the really deep field imaging. So this is sort of the majority of the area of the candle survey. This is 2-orbit HST depth. And on the top, the difference between the top images and the bottom images is that the top images are the simulations without radiation pressure, and the bottom are with this radiative feedback. All right, so here's what the evolution of Sursok Index looks like for this one particular simulation that I showed you in the movie on the previous slide. And we do see this nice evolution from lower Sursok Index to higher Sursok Index as the galaxy evolves. And we see it both in the simulation as well as in these candleized images that are meant to replicate observations. Now, we don't see the trend as easily in the in the simulations without radiative feedback. So this is interesting. We're starting to get more bulge-dominated things when we include the radiative feedback. We can also take a look at the axis ratio of these galaxies. So again, we should expect that they will become rounder as time goes on. So once again, looking at axis ratio that we get from GELFIT, we see a nice trend of increasing axis ratio as the galaxy evolves. And once again, without the radiative feedback, we don't really see that trend so well. It's pretty constant with time.
This is if seen edge on.
This is, okay, I should explain this. Thank you. So what I'm showing you here, the data points here are the average of a bunch of random viewing angles from the simulations. And the error bars on this plot are actually the dispersion between the different viewing angles. Yes. So this is giving you an idea of if you could see the same galaxy in a number of different ways, what the intrinsic error on your measurement of the axis ratio of this galaxy would be. Yeah.
Talk about whether they're disks or not.
You can see actually already, you're hinting at something already. If you look at this image, these images, I took a snapshot around a redshift of 1. And I showed you on the previous, if I go back to the Sursok Index here, I showed you at a redshift of 1, our simulations are being fit by fairly high Sursok indices, but clearly your eye can see that there's a disk there. So the next thing we wanted to do was to actually do a 2-component fit and try to get a better representation of the overall morphology of these galaxies. So let's move forward with that. So here's how we do the the parametric fitting. Here's our original high-resolution image. And if we just take a single Sursok profile and we try to fit this galaxy, you see that the fit's dominated by the central bulge in the galaxy. It tries to fit out that bulge. It does a reasonable job, but you can see it's over-subtracting the bulge and under-subtracting the disk. So the Sursok Index is trying to fit this particular model to the entire galaxy. So it's trying to minimize the residuals over the entire image.
Makes sense?
Sorry?
Did it make sense?
Well,
Did this make sense?
If you do
I'm actually serious.
yeah, it doesn't, because it doesn't look like sensitive profile 4 whatsoever.
right.
Because you have a disk now in peripheral part, and you have a central part. So you need to do it differently. Altogether, it doesn't make.
But I mean, as you know, even in simulations or in observations, there's no well-defined difference, physical difference.
So the problem is that galaxies are more complicated than being single Sursok profiles. It's not a disk, it's not a spheroid, it is a combination of a disk and a spheroid. And so this is the motivation behind doing what we did on the bottom half of the plot here, which is doing a bulge to disk decomposition. And here you can see our model, which doesn't actually look that different by eye to the model of the single Sursok profile. Here we fit a bulge, which contributes roughly half of the light, plus a disk, which contributes roughly half of the light. And you can see the residuals we get when we subtract this model out are much better than the single Sursok profile. And so I would say that we're getting a much better representation of the overall morphology of this galaxy by doing this bulge to disk decomposition. So now we can really get a better handle on the morphology from the high-resolution simulations. We'd like to do the same thing with the observations and see whether we can recover the same types of information. Now, if you remember this galaxy, in the candlelized image, we've gone from this really nice, extremely high-resolution image down to this not-so-nice lower-resolution image. And so it looks very bulge-dominated here. And if you fit it with a single Sursok, you get, again, a pretty high single Sursok index for this galaxy. But you can see there's some residuals left over. So we can play the same trick. We can do a bulge to disk decomposition of this image, even though by eye you might think, how are you ever going to do a bulge to disk decomposition of this? Well, in fact, if you do it, you do get something that is slightly more bulge dominated than we got from the high resolution image. But still, it prefers to include this disk component, which softens the core a little bit and is able to produce a better residual. So,
I mean, if you looked at those in practice, you'd be like, oh, there's not much difference in that.
yeah. Yeah. So we're working, so I talked with Chris.
That's fine, that's how it works.
I talked with Chris Consolis about this to try to determine when it's useful to do this, the two-component fitting versus the single-component fitting, because he has some statistical tests that sort of help him figure that out. But
Well, there's statistical tests that give you an answer, but actually figuring that out has been very, very difficult. I'm sure nobody's got an answer that anyone should be happy with.
right. And so the point of this is that I think what I'm trying to say is that a single Sursok fit is not the be-all, end-all answer. It doesn't give us as much information as we would like to get from both our images and from our simulations.
If you're going to see the disk, it might be in blue light. What light did you fit?
That's a good question. So right now we've only fit the H-band imaging, but we are also working on the other wavelengths as well. And I think that added information will actually help get at the morphology of this galaxy better as well. Yep. All right, so let's move on. So we did this for this, all of the simulations. This is, again, just a single simulation, that original simulation I showed you of the movie. And here we have the bulge to total for both our high-resolution simulations and for our candlelized images. And you can see from the error bars and from the scatter and the data points, yes, there's a lot of scatter in this. And so you just have to be aware of the fact that there's going to be a lot more, a larger error bar in this than there is for something like a Sursok index. but I still think it gives us some useful information. And we see that things, if we do this fit with the simulations, it's quite clear that we're ending up with things that are more bulge dominated near the end. Even though we have disks still at the end, we are getting things that are more bulge dominated. All right, so everything I've shown you up till now is just that single simulation that I showed you in the beginning. And so obviously, if we want to start making comments about how well the simulations in general are doing in reproducing galaxies, we want to look at a wider variety of simulations and compare them to actual observations. And so I stole this slide from one of Joel's previous talks, and this is the work of Mark Mozina, where he looked at where galaxies in the candles observations lie in a number of different planes here. So this is Sursok Index up here, axis ratio, effective radius, and then Sursok Index again down here. And he also divided his sample into clumpy and non-clumpy galaxies. Now we can't do that for the radiative, the simulations with radiative feedback because we haven't had observers go in and actually visually classify these yet, but I think that's in the works for the future. So what Mark did was the previous generation of simulations, the ones without radiative feedback, went in and looked at where they fall on this same on these same diagrams. And here's what he saw. And you can see that sort of in Sursok Index axial ratio, they agree pretty well with the true distribution of observed galaxies. The radius range is a little too narrow. So we were interested in looking at all sort of maybe 20 or so high-resolution simulations that were available to us with the radiative feedback. Actually, there's less than that had radiative feedback.
Verified that this was candlelight.
And this is candlelized, right. So these are not the high-resolution simulations. That's right. This is degraded to look like real observations. And even so, we're still seeing this sort of too narrow of a range in radius. So now we can do the same thing with the high-resolution simulation, with the simulations with radiative feedback, degrade them, make them candlelized, and take a look at where they fall on this plane. And this is what we get. And you can see, I think this is quite nice, so our axis is not quite up at the same level here. But you can see this distribution actually looks pretty similar to me by eye as the observed galaxy distribution, and we now have a wider range in radius as well. It's not perfect, I would say. We're still missing some at the very low radii and maybe some at the highest radii as well. But it looks like we're going in the right direction. We're able to reproduce observed galaxy properties a little bit better with these models that include radiative feedback. Okay, so I introduced this question in the beginning. We know that galaxies are tending towards more bulge-dominated systems, and we wanted to see whether this agrees with simulations and the ones that we've looked at. Yes, it is agreeing. We're getting more bulge-dominated systems. However, without an additional form of feedback like AGN feedback, we're still seeing that there's a lot of star-forming disks at the end of the simulation. I showed you in that image, we had a nice bulge-dominated system, but there was still a disk of stars around it. And so I think this is actually one of the nice cases where the simulations are actually predicting something that we can go out and test observationally. And Joel mentioned this the other day as well. We want to see, are these disks present in the observations below the noise? And people have done this test, and I think that we're probably pretty confident that the star-forming disk doesn't exist, but maybe there's a quenched disk below these that we haven't quite gotten to yet. So the question is, if we take an observation and we stack a bunch of them together, do we get something that looks like it has some kind of disk below it, be it a quenched disk or a star-forming disk? So that's for the future. So I'm just going to conclude here. Like I said, this is all very preliminary results. We're working on doing this for not only just the HydroArt simulations of Daniel Severino, but we would love to do this with other codes as well. And I think that the Agora collaboration is a really great way to do this. We're going to get sunrise processed images from a number of different groups. The code that my students have written this summer is very easily applied to other images. So you only have to tune a couple of input parameters, and mostly it's source extractor input parameters that you have to tune. So what I would say is that these new generations of simulations, including radiative feedback, are doing well at producing the overall properties of galaxies, of star-forming galaxies at least, at redshift of 2, and masses around 10 to the 10 solar masses in stars. I would say that the one potential problem is the existence of these star-forming disks at the end of the simulation, and I think it's probably clear that we need some additional form of feedback to quench these. The question that I would have is that if we do quench these disks, do we expect to see these quenched disks in observations? And can we do that? So what we'd like to do next is to actually stack the candlelized images from these simulations to see how well we recover the underlying disk. How much signal do we need before we can recover these disks? That'll give us an idea of what we need to do, what kind of limits our observations can place on the simulations. And as I said, we'd like to analyze additional simulations produced by other teams in order to get clues as to different physical processes that may be important for producing realistic galaxies. All right, thanks. I'll take any questions.
You showed some Sursok half-life radii. Have you tried seeing where these things lie on the Barrow diagram to see if they look like they're compact star-forming galaxies or compact quenched galaxies, because you don't see that extended disk in the candlelized image?
That is a great idea. We have not done that. We can do that probably today. Yeah.
So I was looking closely at the movie and noted that the early galaxies were quite extended, in contrast to, I think, what we tend to see in real galaxies early, which are these blue compact knots. Do you have a comment on that?
Well, my comment would be that this was a single simulation. And so the other simulations actually look different. You know, I picked this particular one because it had this nice progression in bulginess and et cetera.
I hope you'll look at that.
But yes, we are looking at all of the other simulations as well.
Actually, there's a paper, which you should have received a copy of by now, led by Greg Snyder, that shows the whole sequence of 10 of these simulations with radiative feedback, candlelized and non-candlelized. And in the candlelized ones, you typically don't see the disk until lower redshift. This was actually mentioned by Jennifer Lotz in her talk. In the non-candlelized, in other words, in the higher resolution ones, you can often see the disk earlier. But when you add the noise and lower the resolution, the disk disappears.
Just a quick.
That's a good question. For that movie, they were candlelized, but were they, or sorry, they
No.
were sunrise, but were they candlelized?
They were not candlelized. Those were the high resolution images. Yeah.
About your disks which are not quenched as you think they should be, I think you should consider that your galaxies in simulations are very selected in a very special way. None of them at the end of the day end up in dense region. And none of them are terribly big. So if you look at the real universe in those environments, none of those disks are actually quenched. Right? Or at least large fraction should not be. So it's good that you do not get too many quenched disks, otherwise it's a problem. Yes.
If you're gonna do that,
Yes.
then you don't want those big bulges either. Necessarily.
Only in field you can, I mean, the signal.
You yourself is worried about bulgeless disks, and there are quite a lot of them.
Oh, yeah,
That's all I'm saying.
we have Bowser's. That's no problem.
Not the nose.
depends on mass, just a small one.